So, first talk. Hannes Lowette will talk to you about actors can rule your DDD world. Have fun.
Thank you. Before I start, today is a lot of firsts. It's the first time ever I'm in Berlin. It is the first time ever I'm speaking at KanDDDinsky. And it is also the first time ever I brought my family to a conference. So if these kids are misbehaving, sorry, that's my fault, they are mine. It happened to work out that way. It's a school holiday in Belgium, so I figured I'm going to make it a little bit of a holiday. So it's a bit scary. Usually I only speak to tech people like my people, but now they get to see what I do. So for today, what are we going to do? I'm going to first talk to you a little bit about the problem domain that I used for the examples. Then I explain to you a little bit what I wanted from the piece of software that I was going to build. And then I'm going to explain why I chose Akka.net to build it. And then we'll dive into some of the technical details and see how it all fits together and what can help you when you're building event-sourced systems with actors. So first, what am I building? We're building beersender.net. And why are we building Beersender? Last year we had a very nice stint of conferences like around November, December, and that's where I feel at ease, like talking to other tech people and having fun. And then the world went on lockdown again. I remember when it happened. I was in Norway with Fagif, and in the middle of a conference, they decided like everything goes back on lockdown. And that hit me really hard. And I was really bummed out, and I figured, okay, what am I gonna do? But I'm from Belgium, so what do we do in Belgium? What do we make better than anyone in the world, right? Beers. So I figured if I take a bunch of beers and I put them in a box, and I ship them to my friends, then everybody will be happy, and if my friends are happy, then I'm happy, and this is gonna be awesome. So yes, awesome idea. So I set out and I bought like almost 100 beers, I guess. No, almost 200 beers. I made a nice selection of all local beers, and luckily I have some friends who run a microbrewery, because in Belgium we don't do cans. We do glass bottles, but glass bottles are hard to ship. And my microbrewery friends gave me these boxes that allowed me to pack everything in a safe way so that I could ship these boxes around the world, right? I made 8 boxes, and my expectation was I'm gonna give UPS a bunch of money, and if I give them a bunch of money, they will deliver these packages to my friends. That was my expectation. The reality, unfortunately, was a lot more sad. This is one of the shipping logs of one of the packages. It says things like return to shipper. UPS deemed that I did not have a proper license to export alcohol outside of the EU. So all the packages that were not going to the Schengen region were returned to my doorstep. I got into a discussion with them because they are gifts. I'm allowed to ship gifts. I know this because I worked for a company that makes customs software. So I know very well what I'm allowed to ship. But UPS didn't agree, so I had to go through another shipper and try to recuperate money, and it really wasn't fun. So I was tracking all these tracking codes and providing extra info for customs and going through all the emails. I had to deal with the UPS help desk. Anybody had to do that before? No, UPS help desk is like a special kind of hell in and of itself. You go through 5 minutes of menus and then another 4 to 5 minutes of waiting music. And then if you're lucky, you're gonna get somebody on the line who can read the same info of the screen that you can read of the tracking page, and they don't have any additional info whatsoever. So after all this, I figured like sending beer is tricky, so we're gonna need to make an application to track all of our beer shipments. So we make beersender.net. Why do we call it .net? Because it's not written in VB6. Please stop doing that, like calling your applications .net. We've had .net for 25 years-ish, 20 years. Now, anyway, so I figured if I'm going to build this and make a talk out of it, I'm going to need to use some original design ideas when I built this application. So I got my inspiration from DDD, and we're at a DDD conference, so I don't have to explain to you guys what DDD is all about. What I do want you to remember is that DDD is all about bringing the language that you use with your business as close to the language that you use in your code as humanly possible. And on a high level, we're going to look at all the bounded contexts, and those will probably end up being our services. On a low level, we will try to keep our code as expressive as possible and as close to the reality as we can, right? And the root of reasoning, as you know, are the aggregates, which will piece into the software design that we're going to build. And what we will see, if once you start applying all these principles, once you start thinking in commands and events, you end up with software designs that use event sourcing or CQRS or whatever. So for our commands, for those of you who are not familiar, commands, we state them in imperative form, and they ask the system to perform an action, and the events are what comes from that. It's like something that has already happened and that we already checked. Now, CQRS architecture, what CQRS basically talks about is you should split your write side of your system from your read side of your system. And there's various degrees that you can use that to implement. But it becomes really nice if you pair it with this whole command event way of thinking. You can have a command side, you can have a read side, and if you use the events to project the data in your read storage, then you can go to this ideal situation where all your read queries hit single tables in your database, preferably on an index. And on the command side, you're only dealing with the writes, and you can separate and performance tune two sides from each other. You don't believe me? But you never did. You taught me this stuff, man. He told me yesterday he was going to come and heckle, so you've done your job. Bye, Marco. So, now I lost my train of thought. So you separate the write side from the read side, and that gives you a whole bunch of ways to performance tune your system. It also makes your business logic quite straightforward to write, because you don't have to keep all the read side implications in mind when you're dealing with the commands in and of itself. And that simplifies a whole lot of things on the command side. And on the command side, if you take it one step further, because you could do CQRS with like this with a true database that just uses a CRUD system, but it becomes a lot nicer if you use event sourcing on the command side. So we don't store the eventual state, we store all the events that led up to the state. And that allows us to project the state whenever we need it. So when I was thinking about Beer Sender, I figured it would be nice if I could all these things, if I could put all of that into practice while I'm building it. So I want to have a CQRS system with event sourcing. I want to have very clean aggregate implementations, and I want to have the nicest human-readable tests that I can possibly have. So when I was looking at all this, it's like, okay, this is not going to be that complex, so let's play around with the technology a bit. And for those who've seen me talk before, I really love Akka.NET as a technology. And I think it matches really well with this kind of system. And I'm going to tell you a little bit where Akka.NET comes from and how it matches to all of these concepts. Now, Akka.NET is a .NET port of Akka on the JVM, often used with Scala as a programming language. And the first production-ready system with Akka was 2015, the .NET version, that is. And in that period, we actually got 3 actor systems on .NET in a really short time. We got Akka.NET, we got Microsoft Orleans, just 2 months apart. Orleans was the actor model that Microsoft built to build the backend for Halo 4. And then we got Service Fabric reliable actors, which I would argue are maybe not true actors in the sense that they are usually used. But we got all of these in a very short time. And the reason why we got those in 2015 is because we've been seeing this trend for the last decade where single-thread performance is tapering off. Clock speeds have already stabilized for probably a decade. But what we're seeing now is we get more and more cores. When I was in college, having a single-core desktop PC was a very normal thing to have. We now have these multi-core supercomputers in the pocket of our pants, right? And these actor models, they help us to solve one of the problems of multi-threaded programming. It's like if you have a stateful system, and as soon as you have shared state across threads, that is a problem that is going to be hard to solve. And with an actor model, the advantage is that you're always thinking in the scope of a single actor, and that single actor is always only going to have a single thread, so there are no thread synchronization issues between actors, which makes it scale out really easily. So if you want to max out a CPU, it's a very nice programming model to use. It's also why these have caught popularity over the last 5 to 10 years, because we're dealing with a different set of problems. Now, these actor models, they're all about modeling software after the real world. Sound familiar? That is what DDD is about as well, right? And it's all message-driven, it uses reactive patterns, and this concurrency comes out of the box. Now, where in DDD, the root of reasoning is your aggregates, in an actor model, the root of reasoning is going to be your actor. And an actor is actually just a plain old CLR object that inherits from a base actor class. And the only way you can talk to it is by sending it messages. And the messages go into the inbox, and they are processed in order one at a time. This guarantees that on your actor, you're always only going to have a single thread running. And inside the actor, you have the behavior and your state. Or you could call it methods and fields. It's really not that hard. And because you only have a single thread, there's no need to write any locking around data changes. You know that you're going to be thread safe within the scope of an actor. You never actually hold a reference to the actor itself. We'll see that in a couple of slides. Now, the simplest way to do that in code is inherit from untyped actor. This is the simplest actor that you can possibly write. You just inherit from the base class and you implement the onReceive. And the onReceive gets called for every message that is sent in the inbox. The messages are strongly typed, so you can check what type of message you are getting. Now, for people who come from a .NET or a type-safe background, this will feel dirty. There are type-safe varieties that allow you to register event handlers. We'll see that in a couple of slides. Now, about those messages. Messages don't need to inherit from any base class, but it's always nice to keep your messages immutable. It used to be hard, and there used to be a little bit of ceremony involved. Now we have records in C#, which makes it really easy to implement immutable things. What you have to keep into account, this is not, and this might feel a little bit different than using an event-based system where you have a bus where every message you fetch is going to come from over the network. Inside an actor system, whenever possible, the messages are passed around as object references. So it's really fast. It's actually the same object that is passed from actor to actor until you cross a machine boundary. Then it gets serialized and deserialized. You can choose which serializers it uses. So if you would ever try to exploit the single-threadedness, you could try to change the message while it's being processed. Just don't do that, right? Because it might have crossed the machine boundary, and then you lose the opportunity to do that. The people from Petabridge claim that you can process around 50 million messages a second on a beefy server. I can, on this 6-year-old laptop, reliably get 4 million a second, so I have no reasons to doubt those numbers. Just remember, like, throughput is really good. Like sending a message, the cost is not as high as sending a message over a queue or a topic or whatever. It usually doesn't cross the network, it goes really quickly. So when we want to put these messages and these actors together, we're gonna need a orchestrator, and that is our actor system. And this dates me more than anything. The puppet master in this system is the actor system. This is the Metallica album that I listened to when I was young, so that should like kind of give away my age. The actor system is actually the one that pulls all the strings. It's gonna do all the heavy lifting for us. It's gonna instantiate our actors. It's gonna kill them again when there is memory pressure. It will recreate them when they're needed again. It will take care of all the inboxes and manage those. It will schedule all the threads to process the messages on those actor instances, and it will manage all the other things that make sure that everything pieces together. Now, luckily, creating an actor system is straightforward. We can call actor_system.create and give our actor system a name, and that is pretty much all we need to do to have an actor system running in the .NET process that we're in. What I told you a little bit earlier is that we will never hold the actual reference to our actor in hand. When we create actors, we tell the actor system to use props. And the best way to explain props is it is a constructor pointer. So it points to a certain constructor on your actor class. This takes a params array of objects, so you can pass it any parameters that your constructor needs. And this props object can be used to create an actual actor. And if we tell the actor system to use those props and to make an actor with the name myActorName, what we get back is an iActorRef. And as I told you, this is not the reference to the actual actor. It is a little object that allows you to talk to this actor and send messages to it. You can use the tell method, for instance, to send a message to this actor. And the cool thing about these iActorRefs is they have something called location transparency. They serialize well. You can pass them around the network between actors, and they will always work whether your actor is up or not. And if the actor system has decided to spin down your actor, it remembers the props that it was created with. So if you talk to your iActorRef and the actor system notices that your actor is not there, it will spin it up again with the same constructor and dispatch your message to it. So that's the basic of creating that actor system. And what we've done now is create one top-level actors. But actors can also have children, like these three here, right? Usually I make jokes about children now. What happens, maybe I'll ask this one, he speaks English. If I go to a supermarket with you, and you knock something over, who is responsible? Eventually, you. But if the store manager, who are they going to talk to? To you or to me? To me, right? Eventually, I'm responsible for what my children do. And in an actor hierarchy, that is no different. As a parent actor, you are responsible for your child actors. That is why actors are organized in this tree. So what we did in the previous slide is we created an actor on this level, on the A1, A2 level. The three blue ones, they come out of the box. The root actor, the user actor, and the system actor, they're always there. Underneath the system actor, you find all the thread scheduling stuff and the event bus and all those things. And under the user actor, that is the user space where we create our actors. And your position has to be, your address is defined by your position in this tree, and that has to be unique. That's something to keep in mind. If you don't make it unique yourself, the system will append strings to your actor address. So if you create an actor, this is a parent actor that will create a child. This is the more strongly typed version of the actor base class. So instead of having an onReceive method, we can register event handlers for certain types of messages. And we can actually switch the behaviors on certain messages between, if your actor changes its behavior for some reason, you have an instantiating phase and then a normal operation phase and a shutdown phase. You can actually switch out the event handlers as needed. So this will feel a lot more comfortable for all the object-oriented programmers in the room. Now, creating a child is actually not that hard. Instead of calling the actor off on the actor system, we can actually call it on the context. And the thread scheduling context has a lot of info in it that is useful during the normal operation. It has a reference to the parent actor. It has the message in it. It has the sender in it, so we know which actor actually sent us the message that we are processing, all this sort of stuff. If we do this, this automatically creates this actor as a child actor. If you're creating many actors of the same type underneath a single actor, it's always a good idea, like I did here, to include the ID in the actor name. That ensures that your actor addresses are unique. Now back to this responsibility part. So when I'm in the supermarket and something goes wrong, I end up being responsible. It's the same with actors. If an actor throws an uncaught exception, that exception automatically gets escalated to the parent, and the parent is asked how to deal with this exception. Now remember, this probably happened on another thread, on another actor, so it is not the same as catching an exception as we would normally do in .NET code. There is a strategy that we will implement to deal with these exceptions, and there is a bunch of actions we can take. We can either decide like, okay, this is not bad, and we can recover from this. Let's just drop this message and continue with the next. That is the resume action. Stop is something way more drastic. It kills off the actor instance. It deletes the inbox and it just tells you, okay, this exception is bad, you're done. Don't do that with your kids, by the way. The next action is to restart. And that is actually pretty nifty. It preserves the entire inbox, so that is not getting lost. It does recycle the actor instance. So it destroys the actor instance, it recreates a new one with the same props, and then it tries the same message on that one again. And then if I don't know what to do, I sometimes call my fathers, like, how do you deal with this kind of behavior? How did you do that when I was young? And that is the escalate option. You can escalate to the grandparent, and then the grandparent's supervisor behavior gets called. And you can either apply this to the one failing child, or you can apply it to all of your children. And this becomes useful when you're splitting a huge workload into small pieces and creating actors for every piece. It might be so that the whole workload gets invalidated if one of them fails, and then your supervisor strategy might want to reflect that and apply it to all of the children. Now, implementing that is not too hard. You can you override the supervisor strategy. You do this on the parent actor. And you can use one for one or one for all, or even build your own. And what you can do is you can inspect the exception as it happened on the failing child. And depending on what you get, you might want to use a certain directive. That is what you return, and that is what gets applied to this actor. So that's how that works. Now, I've been talking a lot about actors being reinstantiated, like killed and recreated. And as you might guess, all of the state that is in the fields of that actor, that actually gets lost. That is in memory. So if we want to deal with actors recreating their state when they are terminated or recreated, or even after a system restart, we create the same actor again. There is a persistence library that comes with it, and that allows you to run some sort of event-sourced persistence in the scope of a single actor. What it does, it recovers the last snapshot from the snapshot store. Then it replays all the events that had happened since that snapshot until the actor was taken down. And only then will it start accepting messages from the inbox again. So if you spin up a persisted actor, this is what will happen, and you can start persisting new messages, save your snapshots at will. And you have control over all of it. So the way that works is you have a persistent actor. This is a typed one. There is also an untyped version of this one. And the most important thing is the persistence ID. This needs to be unique across your entire actor hierarchy, because that is the key that will be used to persist stuff and to query it back. So that needs to be unique, because that is and this needs to be consistent. So when you recreate the actor, this should get the same value. What I always do is I group all my state into a state object. It makes snapshotting a whole lot easier, because then you can just serialize the entire state object into the snapshot and to disk and bring it back. Makes the coding and the reasoning around it a lot easier to do. And as you see, we no longer have a receive. We have a command and a recover. The command is a message coming from the inbox, and a recover is a message coming from the persistence store, which means that you're in the recovering state. And you can register different handlers to both of them. The reason for that is mainly because you don't want to repersist a message that has already been persisted, and that is a manual operation, so you might want to differentiate between the two. Recovering from a snapshot, you have to register the snapshot offer event handler for that. And saving snapshot is something that happens out of thread. So it's something you schedule to one of the system actors. And it happens out of thread, which means that you have no feedback whether it was successful or not. So if you want to have that feedback, you register to these two commands, and they're going to come in through your inbox. Usually it's not that bad when you miss a snapshot every once in a while. But in some cases, you might want to have something happen when that happens. Now, the rest of this actor, there's a couple of things I want to show. For instance, like the persist method. The persist method takes in the event that you want to write to your event store. And it also takes the method that will mutate the state. In this case, our handle message internal method, the one that we also call when we're recovering, right? That will mutate our state, and the persist will actually persist it to the event store. We can implement whatever snapshotting mechanism that we want ourselves. We do it every 100 messages here. But it could be, you have full control over what you do with it. There is a timer that can schedule messages to an actor. You can schedule messages to yourself, so if you want to take a snapshot every day or every hour or whatever, you can do that. You can use message counters or whatever trigger mechanism that you find interesting. Now, if we're recovering, we get that snapshot offer, and we can just say, it is already cast to the type that it was saved with. So if we just get it back from the snapshot store, we can just overwrite our state object, and makes things a lot easier. If we want to do something with successful and failed snapshot saves, we register these two event handlers and do it there. So as you can feel, there's a lot of things in here that map really well to the things that I described in the beginning. Everything is message-based. We try to model our software as closely to the real world as we can. The event-sourced persistence is already built in. It is the only persistence model that is built into Akka.net. And there is an event bus, we'll get back to that in a couple of slides, that allows us to do the pub/sub messaging between our command side and our read side. So if we put all this together and we look at a couple of the code details that we could use, disclaimer, none of this is production code. It's something that I built over the course of a weekend. But I simplified some things. but it explains the concepts and the possibilities really well. So if we implement our aggregates the same way that we would use them probably in an object-oriented system or whatever system we use, I try to model them as agnostic as I can. That way I can either run them inside Akka.NET actors or any other process. It makes it easier to reason about. So we'll have two methods, one to dispatch a command. Yeah, I'm formed by the years of doing C#. This interface would not be necessary, but it illustrates the way of reasoning. If we do the check command, where we run a command that returns the events on our aggregate, and we have an apply method that allows us to mutate the state of our aggregate, then it all clicks together really easily. So what we will have is we will have aggregates, all of the data that our aggregate needs, we just keep it as fields inside the aggregate. And on the command side, we can basically have very simple handle methods. And all these methods should do is just return the events that result from this command. I chose on purpose not to mutate the state of our aggregates inside this commands, because it maps really well with the Akka persistence model if we apply them after they have spawned from the commands. So all these do is check a bunch of parameters based on the type of command that we're getting and spawn a list of events. Yield return is very useful for that if you're spawning multiple events. Now, applying events should also be really easy because you know that this has already taken place, so there's no need to check more stuff. We can just apply the result of this event to our internal state of our aggregate, which makes the apply code usually very straightforward as well. And the big advantage is if we make a test class that, where this is my test base when I test these aggregates, it's also nothing Akka.NET related. If we just take a bunch of events that have already happened and we check a command on this aggregate, then we can just check if the resulting events are what we expect them to do. And there's no need to really look into the base class that much, but it leads to tests that we can almost read together with our business owner. And that is the cool thing about this. You can even get rid of the news if you use factory methods, for instance, and then all the words should be almost natural language for a business person to read with you. And this is, for me, always the ultimate goal of bringing events and commands into a software system. It is very easy to reason about and to model with your domain experts and to get to what should the system be doing. If you take tests like this, you can actually write this together with your domain expert and you can validate the entire behavior. So now that we have these aggregates, if we want to plug them into the Akka.NET system, it's actually not that hard to do. We can even build a generic implementation that wraps around that iAggregate interface and that runs that inside an actor. If we look at that, the persistence ID could be the type of aggregate that we're getting and the aggregate ID. That will always be unique in our system. So that persistence ID, we're good with, right? And the aggregate, that just gets created as a new aggregate every time we create the actor, because what we will do is we will just apply all of the events to it that will mutate the state. So there is no need to do anything else but that. And when we get a snapshot offer, we replace the entire aggregate, because that contains all of our data. So if we snapshot, we just snapshot the entire aggregate. And when we get a snapshot actor back, everything is already there. So all that's left for us to do is to make sure that events work well. And if we get an event that is coming from the recover, we just apply it to our aggregate. And if we get a event that is coming from our inbox for some reason, then we still need to persist it. Now, what this apply event does, do I have? Yeah. So that is the snapshotting thing. Now, if we apply an event, all we need to do is dispatch it to our aggregate because it has an apply for all the events that might have possibly come from this actor. Again, the 100 message snapshotting. Now, if we do commands, and this is where the whole thing pieces together, if we get a command for our actor, we can get the events that come from our actor by doing the check command, and then we're going to persist all of them and apply them. And this makes sure that they are always persisted and applied to the state of the actor, because this actor is going to stay in memory. It's not going to be recreated for every command that we get. And this is the loophole where we piece it all together. And then there is the one line below it, the event stream. We'll come to that into a minute. Now with this base actor, for every aggregate type that we have, we can just make an aggregate actor, a beer shipment actor, just like this one, and all of the implementation is already done. We just implement the aggregate interface, we plug it into an actor like this, and we are able to create these actors into our system, and they will behave the way that we want them to behave. Now, how does my hierarchy look like when I start doing all this? In its simplest way, it's going to look a little bit like this. And our aggregates are going to live there. There's going to be a whole bunch of aggregates in there. And there's a bunch of things that we want around it to complete our CQRS system. So first of all, we're going to have an aggregate manager. And the responsibility for this actor is to create aggregates as we need them. So you request a connection with an aggregate of a certain type. And let's say the system's just started up, so what it will do is it will create this actor, it will spawn the whole persistence mechanism to recreate all the state that was necessary if it has existed before. If it didn't exist before, it will just be an empty actor. And then it will send the iActorref for this actor back to the sender. So it doesn't matter, yeah, it's fine, was a time check. So we are getting this, we're sending it back to the sender, which allows the sender to communicate directly with the aggregate actor, so that the aggregate manager never becomes a bottleneck for messaging. And that will create one aggregate actor for every instance of the one that we have. Now the tricky one is the command router. The command router will actually take all the incoming commands of our system and relay them to the appropriate aggregate actors. And what needs to happen there is that one will send the connect requests to the aggregate manager, and then it will start relaying messages to the correct aggregates. This may become a bottleneck, because that's going to relay your entire command stream into your system. So this is a risk. And as you may have already guessed, since these actors are single-threaded, you can never process more messages on a single actor than a single core on your machine can deal with. So once you hit that threshold, you're going to have an inbox that keeps growing and that you can never catch up to. There are ways to solve that. I'll come back to that in a couple of slides. And then we have projectors, and that is the read side of our CQRS system. We can have some actors that we create, and they subscribe to the internal event bus. So all of the messages that we published on the event stream, you remember the context.eventstream.publish, we can subscribe to those messages in different actors, and they can mutate our read storage. Now for read storage, you can use whatever you want. You can do a document database, or you can use a simple SQL, or even Azure Table Store, or whatever you want to use. But these projectors are going to be responsible for filling that data. And then there is the matter of integrating this with external event streams, right? There's gonna be messages like events from your system that need to flow to the outside. You're gonna want to subscribe to certain systems and relay those as commands to your aggregates on the inside. For that, we just make, I call them subscribers here. They integrate between your actors and the outside world. You can use an actor that subscribes to, for instance, a queue, and that reads messages off of that, and that will spawn messages to other actors. All of that works really well. Also there, we can use the event bus to relay things to each other. So about this event bus, it is a very rudimentary implementation of a pub/sub messaging system. You can just publish things to it, as you can see on the left. You can either do that from inside an actor or even from the outside. You can, if you have a reference to the actor system, you can publish on the event stream from the outside as well. And if you want to subscribe to messages, you can use the code that you see on the right. Pre-start is a method that you can use in an actor that will run before it starts accepting any messages, so this registration will work. The only filter that you have is the type of event. So there's no way to easily scale that into multiple subscribers. Everything that is of a certain type will get relayed to this one actor. So there also you might want to solve a bottleneck. And I already mentioned the bottleneck with the command router. There is a mechanism inside Akka.net that allows you to group a bunch of actors and make them respond to a single inbox. And that solves all of the scaling issues where you have a single point in your actor hierarchy, but you need multiple threads to deal with it. And you can have either router pools or router groups. The only difference between them is that for a pool, the router will create its own routees, and for a group, you will create them and pass them to the group. There's, I think, 8 or 9 different routing strategies to choose between your routees. For a command router, something like consistent hashing based on the aggregate ID would be useful. That means that the same routee will talk to the same aggregate all the time, and all the messages that go to that one will end up at the same routee. But you can do round robin, you can do smallest inbox. There's a whole bunch of strategies that you can use there. In code, it's no harder than telling the system that this actor that you're creating with certain props is going to be a router. And that will create, in this case, a round-robin pool with 5 routees. So you will basically effectively have 5 threads that process this one inbox. This is the same strategy that you will probably use on your projections if you're running into performance problems there. I think we're almost out of time. They asked me to thank all of the KanDDDinsky sponsors. These people make this conference possible, so go and say hi on their booths when you're out and about. So to wrap things up, your aggregates go into actors, all your projectors go into actors, all your commands are just messages, and all your events are messages, and the event sourcing is already built in. So in short, I think DDD and actors map together really well. There's very little friction. For those of you who are going to join the open space and are interested to see this in practice, I'm happy to take a couple of hours and mob program this into a system. You will see it doesn't take too much time to do. There is, however, a whole bunch of things that we did not talk about. For instance, if we want to publish that event stream to the outside, we're going to need to hook it up and maybe publish the messages on some kind of WebSocket system or single R so that our UI can subscribe to the event stream. If you want to configure actor systems, you're going to need something called HOCON. It is the Human Optimized Configuration Object Notation. Kind of looks like JSON, but it's not. So that's a mess, especially if you need the 2 for your job. Everything that is clustering. Akka.net is a little bit It's a Swiss Army knife, but you have to configure everything yourself. So as soon as you go into clustering, you have to think about how you're going to shard actors across your cluster. So there's a whole bunch of strategies that you can take there. And of course, you're going to need visibility for your system. There is one paid component in the Akka.NET ecosystem that is Phobos. On version 2, it supports OpenTelemetry, so it plugs into pretty much any production monitoring system you would like to use. Licensing costs are reasonable. I think around 4,000 euros a year for your entire organization. I'm not affiliated with them in any way, by the way. If you want to learn more, there is a great Akka.NET bootcamp on GitHub. It is maintained by the Petabridge people. They are the people who maintain Akka.NET and give consulting with it. They're very knowledgeable. They offer paid training as well. Their blog is a gold mine. This is one of the only products that I work with where I usually find more info on the blog than on Stack Overflow, and that's saying something. I think they really hate explaining something twice, so there's so much cool info on the blog. I'm Hannes. I work for a company in Belgium called Access. That's my Twitter handle and my ICQ number. I'm on a mission to make ICQ great again. We have 5 minutes for questions, but maybe I promised my kids I would call them on stage if they behaved well. You think they behaved well? Yes? Come on up. Two of them are still putting on shoes. So, anybody have any questions? So this is Erne, he's 11. What do you like doing? What's your favorite hobby?
Living.
Living, that's a good hobby. And that's Joren. What is your favorite hobby? Being shy, I think. And there's a little girl in the back somewhere. I think she left. Where is she? She's running down the hallway and collecting gadgets. Yeah, probably. That was to be expected. Questions? For them or for me? Yes?
So for them. So how did you like the presentation of that?
Ooh, how did you like it?
I didn't know a lot about coding, but I learned a lot.
You learned a lot? Good. So you can build this now? Other questions? Now, yeah?
Maybe I didn't understand it correctly, but yeah, thanks. How is this command router actually connected to the actors? So the router must know about which actors can handle the command, right?
Yeah, when you have one of the router instances, let's assume that it's a pool, right? If you have one of the router instances, whenever it receives a command that maps to a certain aggregate, it will ask the aggregate manager, like, hey, I need to talk to an aggregate of this type with this ID. Can you give me the actor ref for it?
Okay.
And then the aggregates manager will have the, I can go back to a slide where we can see them. Oh yeah. So the aggregate manager will then be responsible for creating the actual aggregate actor. But since this is just object references being passed around, all of this will happen snap fast. So even if you're in the scope of an HTTP request, for instance, all this messaging going around is not the worst thing in the world to happen. So the command router will talk to the aggregate manager that will create the aggregate instance, or if the aggregate instance already exists, it will pass the actor ref to the instance back to the command router, and then the router will actually talk straight to the aggregate instances. So as soon as the command traffic really starts, they will talk directly as soon as they are connected.
Okay, thanks.
This is why I said that I would probably, if I have a pool on the command router, that I would use consistent hashing to dispatch my commands to the routees. That means that every instance of the command router will know about a shard of my aggregates, and all the commands that go to that shard, they will all arrive at the same routee. And that way, that is actually very efficient to implement. Okay, we need to wrap up. If you have more questions, I'll be around. Come talk to me in the hallway. I love talking about this stuff. So yeah, please. I hope you enjoyed today. And I look forward to the rest of the conference.